Good afternoon, everyone. Today we are going to discuss gravitation. Yes, you're welcome and good afternoon. Can you hear me?
Good afternoon.
Yes, today we are in for a new element, which is going to be called gravitation. I saw so many girls here, but they are no longer anywhere to be seen. I wanted to kick off when people at least are around 20, because we are studying with the Navisusa girls as well. So basically, the physics we are going to discuss today is what predicts the times or the time durations we have in terms of days, in terms of nights, in terms of years. This is the physics that helps us predict those periods. And it is the physics that tells us how the universe idea looks like, looking at our solar system. And our solar system, I'm meaning the sun and whatever is being controlled by the sun. That is our solar system. And I have an image with me here already, which image has a prediction of this as the sun, and this as Mercury, which is the closest planet to the sun, with this as Venus, with this as the Earth, with this as the Mars, with this as Jupiter, with this as the Sun, and this one as Uranus. Then we have Pluto, and there is another planet which are new ones which were discovered later. But to start with, we need to know the following about our solar system. It has, one scientist was suggesting that our solar system wants to behave like a very giant atom, whereby it has the sun as the central body that is controlling all the other bodies. For example, the sun can control the first body, maybe here is Mercury. Then from Mercury, we proceed to the next body being controlled, and the next body being controlled is Venus. Venus can be here at this time. Then the third body that is being controlled is the Earth. Maybe the Earth is at this point here. Then after the Earth, we have the Mars. Maybe Mars what at this point, at this instant. Then after Mars, like the diagram shows, you have Jupiter, and then the others follow. But some of the key important aspects in this topic or in this area we are going to discuss are the following. One, the distance from the sun to a given planet, R. Yeah? These planets have different radii from the sun. All of them are at different distances from the sun. Reason being, they have different masses. So their mass predicts, one of the predictions of their distances is the masses they have. The bigger the mass, the more the energy the body or the planet possesses. Some of you, we have talked about the Bohr atom, the hydrogen atom, and we have seen how electrons would behave if it was an hydrogen atom. And those electrons in higher orbits, they would have to possess better energy or higher energy. So even here, the planets which are further away possess a greater amount of energy than those ones which are closer. And more so, among the ideas also there is that those planets have smaller masses, those ones which are closer. So the masses reduce as you head towards the sun. Then the masses increase as you move away from the sun. It's like the way you guys see me. You know, most of you know me very well with my size. It is not so easy for me to be pulled by most of you around, but it is very easy for me to pull most of you around. So it is easier for me to attract most of the small-bodied people by pulling them by myself, but it is hard for the small-bodied people to run away from me if I have decided to pull them closer to me. So even this sun, the sun is very big. It is very huge. Actually, the sun, for example, here you're going to see the masses of the Earth. For example, the mass of the Earth is 6.0 times 10 to the power 24 kgs. Then if you look at the mass of the sun is approximately 2.0 times 10 to the power 30 kilograms. When you look at this power 30, you see it has an approximate of times 10 power 24 times 10 power 6 to make the 30. This times 10 power 6 is 1 million. So it means you almost need 1 million Earths to create one sun. That is how big the sun is. It is very huge, very, very huge. So because of its masses and its capacity, its size, it is able to attract all these planets around it when they are revolving due to the electrostatic force of attraction between the mass of the sun and the mass of the other planets. Sir Isaac Newton stated a law which we are going to discuss, and that law is going to be talking about how the force of attraction between two masses helps them to be holding each other. Yeah. So as I was still predicting, these smaller masses, for example, like Mercury. Mercury is very small, but actually Mercury is not as hot as Venus. Venus is bigger than Mercury, very bigger than Mercury in comparison, but Venus is hotter than Mercury. One can say, how? Why? Have you ever imagined why? Or have you ever read about, or could you imagine that the other which is closer to the sun is colder? Yeah. That physics, we shall come to a point of looking at what we call the escape velocity. And the Earth, for example, has one moon. We all know our moon. We have our single moon we always see. This single moon of ours rotates around the sun, around the Earth. But the moon is very cold. That's why you see people going to the moon, they put on gadgets which are warming gadgets. Even the moon has no oxygen. Likewise, also this one has no atmosphere and oxygen that much. So the physics here will tell us the reasons why. When a body has a small mass, or when a planet has a small mass, it has a very low gravitational pull. That's why this topic is called gravitation, because everything rotates around gravity. So the Mercury has a very low gravitational pull, just like the moon. So it does not allow gases to stay on the surface of Mercury. Likewise, also the moon does not allow gases to stay around it, so it has no atmosphere. And for that reason, it is very easy for gases to escape, and thus those bodies will not have a medium of transfer of heat. Hence, they become very cold. So when in Mercury, its night falls. The night of Mercury does not take the same time as we have the one for the Earth. For us, we take 24 hours. If this side it is dark on Mercury, it cools down very fast. Why? Because the gases, because the air which would have easily been warmed up by the sun easily escapes because Mercury has a low gravitational pull. So on average, the average temperature of Mercury is lower than the average temperature of Venus. Venus is a little bit heavy, so it attracts those molecules or those gases, and it keeps them with them. In that sense, it can contain an average warmth due to the gases present. So whoever has no atmosphere, it is a very cold planet, or it's a very cold body, because the gases easily escape due to a low escape velocity or the low gravitational pull a given planet has. More about this, Jupiter. Let me speak about Jupiter. Jupiter is another big planet. Jupiter is big to the extent that Jupiter has, Mars has around 4 moons, I think. Mars has around 4 moons, 4 to 3 moons. I will need to confirm. But Jupiter, as we speak, the last findings, we are predicting 79 moons. If Jupiter has 79 moons, do you know what it means? It means Jupiter is very big. Because the bigger the body, the more it controls other bodies. Our Earth is also okay, because we control one moon, but we are very weak and very light compared to all the other masses that come ahead. Pluto is small, but it is just very far away. That is the advantage it has. Now, more to speak before we can go to the introduction officially. More to speak about these. These planets rotate around the sun. And as they rotate around the sun, they make a complete revolution of those elliptical paths around the sun. When they make those elliptical revolutions around the sun, they make 1 year. The commonest example we know is our Earth. Our Earth can rotate around the sun around 365.23 days, which is approximately our 1 year, which we all know. But other bodies, for example, Saturn has more than 100 years, around 143 years, still rotating around the sun. So meaning no one can ever see a revolution. For the living humans, no one can ever see or can be in position to be alive when this planet Saturn is making its complete revolution. The same applies to these other ones. Even Jupiter takes more. A day of Jupiter, they also spin about their axis. They also spin about their axis like this. We shall also talk about this, which makes the period of a month. A day of Jupiter takes around 6.5 days of the Earth. For us, we know our Earth is 24 hours. Now Jupiter takes 13/2 times the 24. This is 12. Yeah? 12 plus 13 is 144 plus 13, you get 157 hours. Those are the hours Jupiter takes to make 1 day. That you have seen sunlight like now, it takes 157 hours to see another sunlight again once darkness falls. Or from now, like now is what? For 1547. It is 3:47. It takes 157 hours for it to reach the same time again for the following day. So those are some of the predictions we are going to have in this topic. So we shall talk about the revolutions of these planets. We shall talk about the revolution of the moon, especially because now we end up at this level, we zeal the astrophysics to the Earth. But of course, those of us who will go beyond and study astrophysics. We are unlucky in Uganda, we don't have astrophysics as a course unit or as a field of science being taught, because you know it is expensive. But those of you who might go to US or those 5-star countries, you might be in position to join those classes of astrophysics, and you can be in position to enjoy some of these areas. So this is what the gentleman normally calls Chigularuji. So this has opened our class for today, just to show you how these planets look like and how some of them move around, what is closer to the Earth, what is far away, which one takes more time, which one is more massive. One thing you should know, none of them is as massive as the sun. That is why all of them can be controlled by the sun. Yeah. When you look at this image, Mercury is here, Venus is there. Yeah. Venus is here, Jupiter is here, Neptune is there, Pluto is there, Uranus is there, Saturn is there. Saturn, by the way, has a ring of gases. I told you it is very massive. So it is huge. It has a very big mass. It controls very many items, very many moons, very many asteroids that can be rotating around. It can also control gases to the extent that the gases can be visibly seen from space. That is how strong it is. I've told you the bigger the planet, the more energetic it is, and the faster they move. Because if you have the high kinetic energy, probably you're likely to move faster. But however much you're saying they are moving faster, you see those rings of the orbits, they are far away, so they travel very long distances. That is why they take a lot of years to complete their revolutions. So with that, let me show you this other image here. This other image is for, there's an image I wanted, this one. Okay, here it is. Yeah, there is this image I want you to look at. As you see this image, I don't know that, are you seeing that image of those planets? Yeah, that image shows you some of the illustrations of how these planets look like. So if you want to know how these planets look like, the Earth initially was not looking like this blue it has. This blue you see on the Earth, we didn't have it before. Actually, before, it was something like this, coated with white. But the reason why now we are seeing a clear Earth, it is because we have some effects that have happened to our atmosphere, and our ozone layer has been tampered with a lot of, due to a lot of burning and a lot of deforestation. So that means the amount of carbon dioxide component or compound in the atmosphere has increased. When it increases, it is going to bring about global warming, and you're going to be in trouble. So as you're out there as physicists, discourage a lot of burning, discourage a lot of deforestation, or if you carry out deforestation, make sure you carry out reforestation. Those are some of the things that can protect the Earth. Okay, so that is the brief picture of what we are going to discuss. Unless if someone has a question before I officially go to what we are going to call gravitation as an introduction to theory. So we are having gravitation. And in this gravitation, we landed on a gentleman called Johannes Kepler, who has some laws he left with us. And these laws are called Kepler's laws of planetary motion. Kepler's laws of planetary motion. Around 1609 to 1619, that is when he spoke about these laws. Okay? So you can do research via the internet, visit Mr. Google so that you can have more interesting aspects to read about. At least, guys, this is astrophysics, this is gravitation. It is not a boring concept like most of the other concepts you take a look at. I trust that it's really a good concept to visit. Oh, there's one table I wanted you to see. Let me see if I still have it. There's a table I had, which I wanted us to take a look at. Yeah, this table. Let me share it with you. This table has a summary of some planetary facts. Yeah, I'm going to share it on the WhatsApp groups. Then you will see which planet has the greatest speed, which planet has the biggest mass, which planet is having the greatest radius from the sun, which planet is more massive, which one is having a very big gravity, yeah, which one can support life, which one cannot support life. So all those aspects are mentioned in this table. Which one is faster according to the speed? For example, if I talk about the velocity aspect, there is one here which we can see. Let me show you something about velocity only, and we stop at that. Then we go back to our introduction. Velocity, I cannot see this very well here, but let me check it out from my phone. Velocity is line. Okay, velocity. Let me talk about first escape velocity. Escape velocity is line number 1, 2, 3, 4, 5. Yeah, number 5. This is where the escape velocity is 1, 2, 3, 4, 5. The escape velocity of Mercury. The escape velocity of Mercury. This is escape velocity. The escape velocity of Mercury is 4.3. The escape velocity of the Venus is 10.4. The escape velocity of the Earth is 11.2. Those are in kilometers. Venus, if you can run at 4.3 kilometers per second, you can escape. If you're on Mercury and you can run at 10.4 kilometers per second, it is okay, you can run away. on the Earth, here we are. If you're on the Earth, you require 11.2 kilometers to run away from the gravitational pull. If you want to run away from the Earth and go to space and never come back, you should run at that speed. So every planet, every has its own escape velocity. The velocity of escape is that velocity one requires to run at in order to escape from the gravitational pull of the planet. We shall discuss an element as escape velocity on its own. Look at an example of the moon. The moon is 2.4 kilometers per second. When you see people in movies in the moon, they look as if they are flying. Eh? They make one step, but the step is very huge that you can jump from your school gate, maybe to your administration block. Why? It's because the moon has a very small gravitational pull and the moon has a very low escape velocity. So when you jump and go up, it can take you some time to come back. Unlike on the Earth, you jump very fast, you come back very fast. Why? Because the Earth has a very big escape velocity and a very big gravitational pull. All these will be seen in details. When you look at Mars, Mars is what? Mars, its escape velocity is, let me check for Mars here, the figure, I'm not seeing it. The escape velocity for Mars is 5.0. Look at Jupiter. I told you Jupiter is very massive. The escape velocity for Jupiter is 39.5. The bigger the escape velocity, the bigger the mass. So it is very likely that you cannot easily run away from Jupiter. So that means if rockets are to go there, the speed with which they start on the Earth should never be the same speed with which they start when they are at Jupiter. That is why going to some of those planets, we are not very sure of how we can come back. Then look at Saturn. Saturn it is 35.5. Venus, Uranus is 21.3. Neptune is 235. Sorry, it's 23.5. And then Pluto is 1.3. I told you Pluto is very small, even smaller than our moon. Very, very small. Its escape velocity is 1.3 kilometers per second. Yeah, it has no atmosphere. You can't have an atmosphere with this if even the moon has no atmosphere. So that is one important aspect I wanted to share on that table. Another important aspect I want to share on that table is the velocity. Where is that velocity? No, not the velocity. Yeah, it was actually the escape velocity. Okay, so with that, we can now go back to our introduction and begin with what Kepler suggested. So this gentleman, Kepler, suggested for us 3 laws. One, we have what we call the elliptical law. The elliptical law. We have what we call the harmonic law. Then we also have what we call the law of equal areas. So the elliptical law states that if you have a sun and then you have an orbit of a given planet, maybe our Earth, Kepler suggested that all planets revolve around the sun in elliptical paths or describe paths which are around the sun as one single focus. So meaning all those planets I've talked to you about in those illustrations, they are all having the sun as their main focus. And when they are moving around, they are moving in elliptical paths, or they follow what we call ellipses. Those are, I trust most of you are doing mathematics, all of you actually. And I know that in mathematics, we shall discuss what we call in pure math, conic sections. And there we shall see what we call an ellipse and what we call a rectangular hyperbole and a parabole. You've discussed a circle, I guess. So the ellipse has an equation, which is an elliptical equation. So that elliptical equation was predicted by Kepler, and he came to see that all planets that are revolving around the sun as a single focus do take or do follow elliptical paths. Then the second one was what we call the harmonic law. The harmonic law was predicted by Kepler, stating it in a way that, let me state the first one. The first one was the elliptical law, which was saying all planets describe ellipses or elliptical paths around the sun as one single focus. However much you'll get the notes, I have to write some of these as one single focus. So all the planets are focusing on the sun. Then there's another new planet called Eris. It has an orbit. The orbit is funny. All these others, the orbits are like this. If you take a look at them, now the other one, its orbit is like this. That new orbit, that new planet which was talked about. I'll see if I have it shared already in my images so that I talk about it and you appreciate the work of the astrophysicists. Now, the second law, which I'm calling the harmonic law, it says that the squares of the periodic times of revolution of planets around the sun is directly proportional to the cube of their mean distance apart. What does that mean? That means that if you go back to our images and look at the way we have been seeing these elements, and you see how actually how the planets have been revolving around the sun. Remember, we said here we have here what? Mercury. Then we have here Venus. The distance of Mercury from the sun is R1. The distance of Venus from the sun is R2. The distance of the Earth from the sun is R3. The distance of Mars from the sun is R4. Now, the period the Earth takes, which is 365 days, the square of that period is directly proportional to the cube of the distance from the sun to the Earth. That is what this law predicts. This is what the harmonic law states. That the square of the period of revolution of the planet where? Around the sun. The years it takes to move around the sun. The square of that period is always directly proportional to the cube of the mean distance apart. Okay? I hope you have understood that law. Come to the third law. The third law of equal areas states that the imaginary line joining the sun and the planet moving, sweeps out equal areas in equal time intervals. What does this mean? We need to show this on an illustration. Where is my illustration? My illustration, where are you? Please come out. Let me show you this illustration of what I'm trying to mean. Okay. Where are you? Sorry for the delay. Okay. Yeah. Okay, let me share with you this. Now, do you see that blue patch, guys? Hope all of you can see that. Now, if a planet was here, my color red, where are you? If the planet was here, then it moves and reaches here. And it takes a time of 1 month. And this same planet, this is position A to A prime. And this same planet comes and moves from position B to B prime. And it also takes here 1 month. Then the area here, area 1, is supposed to be equal to area prime, area 2. So the law of equal squares says that the imaginary line joining the sun moving, or the imaginary line joining the sun and the planet moving, sweeps out equal areas in equal time intervals. So sometimes some books draw it like this, to have this as the orbit. Then the imaginary line is drawn in this form and this form. So that you look at the area as this is the area and as this is the area. So whereby if it takes 1 month here and also takes 1 month here, this area swept out in 1 month on this side is the same as the area swept out in 1 month on the other side, assuming you're considering the same imaginary line of travel. Or the same, you're looking at one planet, which is moving in a given space of period from one point to another, taking an equal time, then it will cover the same area, even if it takes the same time elsewhere along the same path. So that is the law of equal areas. So it states that the imaginary line joining the sun and the planet, this planet, remember, is moving around the sun. That's why we say this, joining the sun and the planet moving, sweeps out equal areas in equal time intervals. So any questions on these laws and the introduction so far before I can move forward? Do you have any questions? If no questions, this is when we come in with what we call the Newton's law. You know, one of our greatest physicists is Newton. Newton's law of gravitation. So Sir Isaac Newton came in with a law which suggested that the force of attraction between the two bodies or between any two bodies is directly proportional to the product of the masses of these two bodies and is inversely proportional to the square of their mean distance apart. Now, this is a law of attraction. We all know the law. Who knows Coulomb's law? Can someone state for us Coulomb's law? You have here 6s, guys. You must be knowing Coulomb's law. The force of attraction between two charges is directly proportional to the product of the charges, inversely proportional to the square of the charges. Now here, Newton came and suggested a law which he predicted that the force of attraction between the two bodies is directly proportional to the mass of these two bodies and inversely proportional to the square of the distance between these two bodies. May I always give these examples and relate them with the day-to-day lives. If you are having an affair, yeah, of course, some of you have affairs. Lugasa, Fatuma. No, I'm not saying you have, but you know what I'm saying. That you might be having someone who you love, but because of the distance you're at, you're in Nabisunsa, the person is in Imbalala. You are in Guru, the person is in Kenya. You are in USA, the person is in Uganda. that force of attraction, the more the distance increases, the rate, when you look at the fractions, when the distance increases, the force reduces. That is why you hear people praising people who have managed to succeed in distant relationships. Why? A very big percentage of those relationships break. They collapse. Someone cheats, someone gives up, someone someone. Why do they collapse? It is because the force between them of attraction is very small. Their love reduces every other day. Chances are very high for that love to reduce. You know, love is an example of force of attraction because of the different parameters. It can be beauty, it can be money, it can be weight, it can be smallness, it can be richness, it can be so many things. But the bond which brings the two people together is because of attraction. So the law of attraction crosses to Coulomb's law. The law of attraction crosses to Newton's law of gravitation. Then it crosses to day-to-day life activities, like falling in love, like having a relationship with your parents, like having a relationship with your brother. You love your brother. There is a force between the two of you that attracts you. It is also within this law. Newton predicts that, yes, these two guys are in love with each other because they are one, lovely friends, they are one, cousins, they are brothers. If you have a brother who you have never seen, who your father gave birth to maybe in Nigeria and you're in Uganda, my friend, you can even take 10 years without even getting to know what happens with him. Why? It is because of the distance between you and him. That distance predicts the bond you have, predicts the force of attraction you have. So here came Newton, suggesting that a body will attract any other body with a given mass, with a given force, whose magnitude is directly proportional to the product of the masses and inversely proportional to the square of their mean distance apart. Let me also write it down for easy follow-up. So a body will attract any other body with a gravitational force. The gravitational force whose magnitude is directly proportional to the product of the masses of the body, of the bodies, and inversely proportional to the square of the distance of their distance apart. Okay, so that is what Newton's law is, and that is why it is in this line of this mathematical expression. Now, be very vigilant. We are commonly going to use capital M to stand for mass of the bigger body, and then we use small m for mass of a small body. Before I can go any further, do you ever ask yourselves, you know, the earth is like this. Where is my diagram? Okay. You know, the earth is round, as you can see. Yeah? But do you ever ask yourself this question? Why doesn't this water pour out? Why doesn't this water pour out? Oh, why when you're on the lake, you see as if the earth is ending somewhere. The water is ending. But as you move further and further, it continues to go also further away. The horizon keeps on curving inwards. It's because also the water is also a body on the earth. But this water is a very big body. Which body is getting attracted to the earth? Which earth is also a very big body? So the force of attraction between the earth and the water is very huge, that this water cannot go up or cannot fall down like you're thinking. One live example I normally give. All of you know ants. When ants are walking on your body, you just imagine. You don't have that attractive force to clearly behave like the way the earth behaves on us. Because even someone can ask you, but excuse me, teacher, why do we jump and come back to the earth? Why is it that people here, they see as if they are standing normally? Even us down here, we see we are standing normally. Even these ones this way, even these ones this way, even why? You ever ask yourself those questions? Those questions can be answered by this gravitation knowledge. It is because the earth, one, is very big. Two, if it's very big, it is very massive. If it is very massive, it has a very big gravitational pull that at any one point you're at, you will feel the same gravity, almost the same gravity. Gravity can only vary when you get closer to the equator. We shall also reach those points and talk about them. Yeah, but otherwise, at any one point, everyone will see as if they are standing upright on the earth. You will not tell people that, hey, for us, we are in Uganda, in Africa, for us, we are upside down. No way. We are all falling back. We are being actually pulled towards the center. The forces of attraction are pulling us towards the center of the earth. So even this ant, which is walking on your body, bam, it sees you as a very huge body. But you are not huge enough. You know why? It can walk the entire body of yours. Not even in one day, not even in 1 hour, and finishes it. But you walk the whole earth in 1 day. So your force of attraction between you and the ant is very small. That is why the ant can go away. But if our force of attraction was very huge, then the ant could not leave our body. That is why we are on the earth and we are stuck here. People have designed rockets and space vehicles to go in the sky. You saw even they have designed, this man for Amazon has put up a company for taking people to tour as tourists. Then one of the guys who was acting in some space movie, is 90 years old. They went last week. But for them, they didn't go to space. They just went until they finished the atmosphere, and then they reached a region of no gravitational pull, and then they experienced weightlessness. They went there just for 11 minutes, and they experienced weightlessness for 3 minutes. Then they came back. It was a very lovely experience for the physicists. But what I wanted to bring out of that is that still, if the rocket was not having the capacity to overcome escape velocity, even these aeroplanes we see, the aeroplanes leave alone they're midges, they are drones, they are midges, they are those other special planes which can reach the sky and go beyond the atmosphere, but very few. But most of them, the reason why they cannot go beyond the atmosphere or away from the earth, it's because they do not fly at escape velocity of the earth. Meaning, if you can run for 11 kilometers in 1 second, you estimate 11 kilometers anywhere more than 5 miles. In one blink, you have reached 5 miles. Another blink, 5 miles. Then with that, you can run away from the earth. Besides that, we shall all stay. So, this earth can pull the water. That's why the water is not falling off. This earth can pull all of us. Everybody, you see, even the birds. You can think they are flying, but they can't fly beyond a given limit of the space because when they try to do that, their gizzards are the ones that help them to breathe. So their gizzards cannot contain the air pressure up there. You have atmospheric pressure. So those differences in pressure, when they're up there, the air up there is cold and more dense. The air close here to the earth's surface is warmer. So it is in motion and it is not as dense as the air up there. So they easily live along or close to the earth's surface where they can easily breathe the warm air from. So all that is physics. So though our friends of biology will come in and say, hey, don't think we are also not there. Now, when we leave that, we can go and then talk about how they can ask you to use Newton's law to predict Kepler's harmonic law. Yeah, a question can be set. But before I go to that question, we have seen that Newton's law of gravitation is directly proportional to, the force is directly proportional to the product of the masses, inversely proportional to the square of the distance apart. When you remove the proportionate sign, we shall get capital G M out of R squared, whereby capital G is the constant of proportionality in Newton's law, which is called the universal gravitational constant. Universal gravitational constant. It is a constant for all planets and bodies in space, and its value is 6.67 times 10 to the power -11 newtons per kilogram squared, meters squared. Sometimes they can ask you to derive its dimensions. Then you make it the subjects and say dimensions of force and R squared over dimensions of capital M and small m. Of course, this will predict force is meters, which is M, LT power -2. R is in meters, so it is L squared, all is over M squared, M squared, okay, because of MM. Then you can lose one M, and the dimensions will become L cubed per T squared per M. Okay, this was, that is how we can derive their dimensions of physical quantity. I mean, their dimensions for capital G. And then from there, you can see that you have per kilogram. Then you can get it in terms of meters cubed as SI units per kilogram per second squared. Okay, as SI units in terms of kgs and meters and seconds. Now, when they ask us to predict Kepler's law, coming from Newton's law of gravitation, then when you look at a body, for example, the sun, and another body, for example, the earth, and we have seen these bodies have a distance r between them, then as the earth moves, we assume it moves in a circular path. Now, here is the return of centripetal force. Whoever missed, those are your problems. Yeah? So, when the earth is moving around the sun, we assume, this is assumed to be what? Circular. So if it is assumed to be circular, we are going to experience centripetal force, which is mv squared over r. But this centripetal force is coming as a result of having what we call the force of attraction, which is capital F, A. Therefore, the centripetal force with which the earth moves is provided by the electrostatic force of attraction between the bodies. Therefore, the centripetal force is given by mv squared over r, and then the force of attraction is capital GM. Now, this is the gravitational force of attraction. This is gravitational. Electrostatics is in Coulomb's law. This is gravitational force of attraction. Capital GMM out of r squared. Because the moving body is the earth with small m, whereas the sun has capital M, then the moving body is the one that experiences centripetal force. And with this reason, we shall have v squared. I lose one r here to this r. So v squared will be equal to capital GM, capital M, out of the radius r. But because the body is moving in a circular path, the velocity of the body is defined by omega r. for bodies moving in circular paths, whereby omega is also predicted by 2 pi out of the, 2 pi f. But if you don't use frequency, we can get 2 pi times the period, and divided by the period of revolution times the radius. So if 1 squares the velocity, it will become 4 pi squared over r squared over the period squared. Thus, when I substitute, I will realize 4 pi squared r to the square over the period squared, and this is going to be giving us capital G, capital M out of r. When we cross multiply, we shall have period squared is going to be equal to 4 pi squared r squared times the r across divided by capital G, capital M. With this, the period squared is going to be 4 pi squared r to the cube divided by capital G, capital M. And this is the equation for Kepler's harmonic law. How do you confirm? You confirm by saying period squared is actually equal to, when you look at the 4 pi squared over the capital GM, all these are constants times r cubed. Remember, this capital M is the mass of the big body, which big body in this sense, if I look at the Earth and the Sun, is the Sun. Its mass is constant. I showed you you need almost a million Earths to get to the Sun. G is the universal gravitational constant, which is a constant. Pi, everyone knows pi. It's the usual pi, 22/7. The 4 is a value, so the whole of this is a what? Is a constant. So if it's a constant, then the period, its square, is directly proportional to the cube of its mean distance. Hence, the proof of Kepler's harmonic law, originating from Newton's law of gravitation. Do you have any questions before I can proceed? Any questions? Okay, if no questions, means learners are comfortable. It is from here now that we can go ahead and predict the mass of the Sun. We can predict the mass of the Earth. We can predict the density of the Sun. We can predict the density of the Earth, and so on. So, estimation of the mass of the Sun. So you can be there wondering, if you're speaking to people who are not physicists, and you tell them that we know the mass of the Sun, don't you think they will call for an ambulance to take you to the mental hospital? But it's good I'm speaking to people who can predict, who can get to know the physics we are talking about. So the mass of the Sun can be estimated by regarding the Earth to be the planet that revolves around the Sun in a period of 1 year. Yeah? So if we assume, though the assumption is true, the Earth of mass small m takes 1 year around the what? Around the Sun. Then we are assuming the Sun has a mass capital M, which we need to find. Then we have seen that if this is the Sun and this is the Earth, we measure the distance r from the center of the moving planet. So we measure the distance r from the center of the Earth, as we shall see. So in that sense, the distance from the center of the Earth to the Sun is 1.5 times 10 to the power 8 kilometers, which is approximately 1.5 times 10 to the power 11 meters. All these are constants, so no need to worry much about them. But as we have seen, as the Earth moves around the sun, it moves in a circular path. If it moves in a circular path, it experiences centripetal force. So if it experiences centripetal force, the centripetal force is provided by the gravitational force of attraction between the Earth and the sun, which is got from Newton's law of gravitation, which is capital GMM out of R squared. When you lose R, we shall still now be in position to make capital M the mass of the sun, the subject. Okay, let me maintain the MS here so that people have it clearly seen that this is mass of the sun. Is going to be equal to V squared times R divided by the universal gravitational constant. Remember, I showed you that V squared was 4 pi squared over the period squared. So the mass of the sun is actually equal to 4 pi squared out of the period squared times R to the cube. Remember, R is the distance between those two bodies. So we know R, I've given it to you. The period is 1 year. 1 year times 365 days. So the period is 365 what? Days. But we need to work in SI units, so we shall convert the days to seconds. So the mass of the sun can be got from 4 pi squared times 1.5 times 10 to the power 11 cubed divided by the period of 1 year, which is 365 days times 3600. The 3600 comes from 60 minutes and 60 seconds. The 60 minutes are in 1 day, times 24, because each day has 24 hours. So the 24 hours, 1 hour has 60 minutes, 1 minute has 60 seconds. So that's why I multiply by 3600. Then times the universal gravitational constant, which is 6.67 times 10 to the power negative 11. There is a challenge here also. We need to have a very smart calculator, which we can press and command as we want. But the period, remember, is also squared. So can you now simplify and press your calc and give me the answer? 4 times 22 over 7, this one is also squared. Times 1.5 times 10 to the power 11, this is cubed. Divided by 24 times 365 days times 3600, all this is squared, times 6.67 times 10 power negative 11. Someone predict for me the answer. Our time is up. Shall stop here and we shall start from the mass. Oh, I'm going to give you an assignment. You go ahead and look for the mass of the sun, of the earth. Okay, I'll do it. I see you don't know the moon. Someone give us the answer. Why are people quiet? No one has mentioned any word ever since I began talking. That is strange. Are you understanding so well? Or you're enjoying the lesson? I don't know. One of the, or you're not getting anything totally. One of the three is correct. Or two of the three is correct. Okay, someone press the calc rightly and get us the answer.
Two point.
2.1.
2.06.
Times 10 to the power. Times 10 to the power. Okay, they don't hear your answers. Someone has come to the book. Times 10 to the power 30 kilograms. Correct. So that is the mass of the sun. They can ask you to find the mass of the sun. Okay. So Kyra, I don't know that Kyra has attended. She has to send us more notes. So I'm going to send you some notes right now. But she'll also send us more notes. And then
I'm here.
you send the notes to the group. Okay. From Gravitation.
Okay. Yeah.
My boys and my friends from the other side, are we okay? The smaller group. Hope all of you have enjoyed the lesson because I've not got any question. I don't know. You leave me in suspense. Yeah. unless if some people never attended.
The lesson was fine. I personally, it was the best lesson ever.
Sure. Okay.
No questions asked.
Okay, please.
The
Thank you.
lesson was okay. It was good.
Okay.
The lesson was good.
Kale, so we meet next Wednesday for the same. And please do some reading so that you come when you're somehow updated. So that I don't speak alone. You come with some ideas to consult on. Okay, with that, let us call it a day and have a wonderful evening. God bless you.
Thank you, teacher.
Anytime.
Thank you, teacher.
Welcome.